go. So it's September 2018 and we are here today with Charles Moore, the inventor of the Forth programming language, and we're here in Edinburgh on the Firth of Forth, overlooking the Forth Bridge, which is a very nice and appropriate venue of Forth. Welcome to Edinburgh, Charles. Is it okay if I call you Chuck?
Chuck is fine.
Chuck is fine.
Happy to be here.
Excellent. Chuck, I thought because it's the 50th anniversary of Forth, it's clearly a landmark, it would be appropriate to go back to the beginning and do a kind of a retrospective interview, take you back all the way back through the journey in your life that has been Forth up to the present day.
Okay.
I thought I'd begin, if I may, by taking you right back to the beginning and ask you when and where you were born, where you come from in the United States.
I was born about a week ago in 1938.
Okay.
9938 engraved in my memory. In McKeesport, Pennsylvania. That's a suburb of Pittsburgh.
Okay.
My grandfathers were involved with the steel industry, of course, because that was what Pittsburgh was. And then we moved to Erie, Pennsylvania, on the beautiful Lake Erie, which died and got reborn. And then moved to Flint, Michigan, where I grew up.
Okay. So you would have gone to school in Flint, Michigan and
Went to
graduated.
Flint Central High School. And Flint was in the news recently because of water problems. And in the course of hearing about them, I learned that there are two high schools now in Flint, neither one of which is Central High School, so I guess it went away.
Okay. And what about your education? Can you talk a little bit about your...
I went to MIT.
Okay.
I was going to be a civil engineer. And I got there and started taking courses in like calculus and decided I liked physics. So I was going to become a high energy physicist. And nuclear physics was a topical subject at the time. And there was a little article in the Flint Journal saying that I went to MIT to study unclear physics. They had transposed the first two letters. But eventually I got a Bachelor of Physics from MIT. Then I went to Stanford for a couple of years, going to become a mathematician, because the part of physics that I liked was the mathematics. And that didn't pan out so well because I really was interested in computers. And the mathematics department was not the place for computers.
So where did your interest in computers become established? At MIT prior to going to Harvard?
Started at MIT.
Right.
I was kind of bored with my coursework, so I got a part-time job at the Smithsonian Astrophysical Observatory, SAO. And they were in charge of Moonwatch, which was going to track the first satellite optically. And that got upstaged by the Russians, who launched the satellite a year earlier, and Moonwatch was in a frantic scramble to try to track their satellites.
So was this late 50s?
It was 57, 58.
Right.
So I got a job running a calculator to calculate observing positions for each of the observing stations. And whilst I was calculating, one of the other students from MIT pointed out that I could write a Fortran program that would do all this work for me.
So you were making the calculations by hand?
Yes, with a Frieden calculator. And so I did.
So did you know Fortran as a language prior to this, or did the spark was ignited when your colleague mentioned this and you had to go away and learn Fortran in order to do it? Right.
I read a Fortran manual and started punching cards, all without authorization. When I finally got a program that could calculate these things, I told my supervisor, and it went up the chain of command, and they said, do it. And so this was called Ephemeris 4, and it was in early 1958, and produced reams of printed output, some of which got teletyped to the various stations. That was a lot of fun. Of course, it paid havoc with my grades. I was working 40 hours a week instead of studying.
Okay.
But it was fun.
Yes. Tell us a little bit about the computers that you were working on then, that time.
This was the
57,
first
58.
computer that MIT got. And Smithsonian was run at Harvard. So there's a Harvard-MIT cooperation. And that was the IBM 709, which was upgraded to a 7090. It was a 36-bit computer, which is curious because half of 36 is 18, and my current computers are 18 bits, so it all goes around circles. This was a computer center where there was a glass wall to keep the spectators out of the computers. And I got to go through the glass wall and actually hand my punch cards to the operator who would put them in a hopper and run the computer. And eventually I got to put them in the hopper, but never got to push the buttons on the computer. Those were the days. It was very informal. I could work third shift and get immediate turnaround, whereas otherwise it might be a day or two.
Right. A day or two to find that there was an error in your program and you had no output.
Yeah. My card deck was about so long, about 2 feet long. It had to be compiled, which took a long time, minutes, half an hour. So I added the ability of the program to read input cards to tell it what to do. So I didn't have to recompile the program, I could just initiate the input.
Right, okay.
And that was really the first tentative step toward Forth.
I was going to say, that does sound like a little spark there of recognition. Hey, this is a good way of doing it.
Yeah. As I recall, it didn't have a stack. The interpreter would read the cards and do things, and it had to read parameters and store them away. But it didn't have a stack yet. The stack came later.
Okay. Okay. So that's a neat sojourn into my notes here, which I'm calling pre-Forth, the very first
Pre-Forth.
Pre-Forth. It's fourth gym, but not as we know it. I've read somewhere that you invented Forth perhaps absolute gritted teeth to a certain extent, purely because you were unsatisfied with your experiences and just trying to get work done. So Forth was quite a pragmatic solution to an accident problem.
Yeah. Well, just for continuity,
Yeah.
when I went to Stanford, I got a job at the Stanford Linear Accelerator Center. And there I wrote a program to steer the electron beam. It didn't exist yet, but it was being designed. And so this is another precursor to Forth, and it had a stack. Again, I had the input deck, input somehow, that I could customize to modify the program. And it had a stack and parameters and function calls and things like that in order to accomplish this. And when I left Stanford, I went to New York City, the Big Apple. If you can make it there, you can make it anywhere. And I was a freelance programmer. I would hunt for programming jobs. And
So you just went out on your own, you just said, I'm just going to do this.
I wrote letters to every company in Manhattan that seemed likely to want to use computers. And I got maybe a 1% response, but it was enough to keep me alive.
Right.
And one of those jobs was programming a mini computer in one of the high rises.
What year was this? Approximately.
This would have been 62 or 3. Is that right? Yeah, 65, say, around then.
Were you married by then?
No, not yet.
Okay.
And it was a very interesting project. I was programming a gas chromatograph. Again, these were one of the first gas chromatographs on one of the first mini computers. And the programming medium was paper tape. So I found myself up on the 11th floor of this high rise on a Saturday night, feeding paper tape into a reader which tore it. And so I needed to tape the paper tape together to patch it. But I couldn't find the tape. I forget what I did, but I was really angry and I said, there's got to be a better way. And I finished that project and did other projects again with interpreters that led me to, again, feel there ought to be a better way. But I didn't have any resources to do any more than that. So that was pre-Forth. Then I went to, then I got married.
Okay.
And got a job at Mohaskell, a proper job which would pay the rent.
Right.
And Mohaskell made carpets. It was a major carpet mill in Amsterdam, New York, upstate, on the Mohawk River. And there I was programming a B5500, Burroughs mainframe, one of the exciting computers of the day. And Mohaskell worked in COBOL. And they wanted an online order entry system. And they didn't exist at the time.
I was going to say, that sounds like quite a tall order for the hardware.
This was around 1968. This is getting into Forth history. So I programmed the B5500 as a time-sharing system using Forth. This was the second Forth. The first one came a year earlier when I was given access to an 1130 IBM mini computer. It was desk-sized.
Okay.
And I was tasked with demonstrating that the 1130 driving a 2250 graphics display would help them design carpets. And I did so, and invented Forth in the process. I wanted a fast, responsive ability to drive that graphics display, which Fortran couldn't do. IBM had Fortran packages that did a bad job of driving it, and I did a good job by writing Forth.
So you presumably would have experimented with the Fortran package and its associated software for driving the display,
Right.
and determined that it was inappropriate for the task at hand. So was it that forced you to sit down? I mean, what I'm thinking is, you say Forth emerged from this, or this would be, so I would recognise it, would I, as Forth, if I was to see some source code written in that first Forth system?
Yes.
I would recognise it as Forth.
No. The symbols were all different. Where now we use fetch and store, for some reason I was using the cent sign, a little C with a line through it. I don't remember what it did, but all of those symbology were different than now.
And that was that just in an effort to be economic, with byte storage, screen space, space on paper?
Well, that was the reason for the symbols, yes. They were abbreviations for words that otherwise would be kind of tedious to type. And they gradually went away because they were just too cryptic. The ones that are left are fetch and store, which are so common that they deserve to have a single character representation.
So, did you sit down at that point, having determined that the Fortran system was not suitable, with almost a clean sheet, and to say, I'm going to make my own language? Or did you already have some inklings of what the ingredients that you would put in to make a suitable language, which we now know as Forth?
I knew what I wanted to do because of my experience at Stanford and MIT. This interpreter I had written was basically what I did at Mohaskell. I updated and expanded the interpreter to give it conditionals, to give it looping capability, but it was still an interpreter. And it was perfectly adequate to generate the machine language for the graphics processor. So it was a cross-compiler, if you will.
Yes. So the output was machine language.
Yes. And I had thought I had written Forth in Fortran, but that is not the case. I had written Forth in assembler, in the assembly language for the 1130. This was pointed out to me recently when people got interested in the 1130 again for some reason. Then the carpet design was not successful because it didn't include color. It was a black and white graphics terminal. And when the management realized that, they sort of lost interest in the project. When the order entry system was just in sort of beta testing, they lost interest in that also because of an economic downturn. So the whole Mohasco experience kind of died away. And I went looking for a job.
Should we break there?
Yeah. Yeah, can do.
I went looking for a job.
We're rolling.
So Chuck, you mentioned in the previous segment that there was a bit of a downturn at Mohasco, and you were out of a job. You were looking for a new job. So what's happened next?
I don't know how it came about, but George Conan offered me a job at NRAO.
What year was this?
Sorry?
What year was this?
1971, something about that.
Okay.
70, 71.
So you were married by now, and you presumably had a family.
I had a little baby, yep.
You had a baby, okay.
And
So it was important to stay in work, clearly.
George had known of my work at MIT, I think, and he was impressed by it. So he offered me a job programming a data system to be attached to the 36-foot radio telescope in Tucson. This work was in Green Bank, which was near Charlottesville. Charlottesville was the headquarters. Charlottesville, Virginia. And so I started programming, I forget which mini computer, but it was a new mini computer. And I took the EuroForth, which I had developed at Mohasco, and ported it to this mini computer. But this was a great leap forward in that I figured that EuroForth could compile instead of just interpret.
Mm-hmm.
And it would be much more efficient that way. So the EuroForths I developed at NRAO were much faster and not quite machine speed. This was not a subroutine threaded system, but it was indirect threaded code, and it was fast, and it was totally appropriate for the 16-bit computer.
So did you arrive at the indirect threaded approach through experimentation? Did you try maybe tokens?
No, it's merely the first thing that occurred to me.
Okay.
And then later, these notions of direct threaded code, which I don't think I ever used, and then subroutine threaded code, which is what I use now. And maybe there was even a fourth version of interpreting. But indirect threaded code, I don't think it was original with me, but I had never heard of it.
Right.
And
Okay.
this data collection system was a big success because it let the astronomers look at the data while it was just coming out of the telescope. I thought that would be fine. I thought they would analyze their data and go home. But no, they didn't want to do it that way. They wanted to take the raw data home with them and reanalyze it. But this gave them a first quick look at it. And it was successful enough that the next year I was programming the telescope as well as the data system so that they could be more closely coupled. And that was a great success.
Was that on the same machine? So the machine that was doing the data acquisition was also controlling the telescope?
No,
Physically?
there were two separate mini computers.
Okay.
And they were connected with a bitbang serial link. I was really impressed by the opportunity to steer this gigantic telescope and get this cutting edge data. This was the time of what do they call it, molecular spectroscopy. They were detecting molecules in deep space for the first time. And it was exciting. I spent all the time I could at the telescope, but really I had to do a little work back in Charlottesville. We got to work on the telescope in the summertime when there were thunderstorms and telescope maintenance and things like that.
So the fourth system that you designed there, that would be what people such as myself would recognise as fourth.
Yes, very much so.
And was this fourth system native to the machine or running on top of vendor supplied kernel or operating system?
No, these were all native fourths. I don't remember how I got the first version to run. I must have had to bootstrap it somehow,
Right.
but I forget how that was. As soon as it got bootstrapped onto the mini computer, then it could recompile itself and cross-compiled for the telescope. It was then standalone. And that was always my goal, to get a fourth that would be self-sufficient.
And these were disk-based machines by then, I presume. They weren't.
Sorry?
They were disk-based machines. They weren't tape or maybe they were.
No, I think they were tape. They were magnetic tape.
Magnetic tape.
But I forget what the boot mechanism was. I don't know that there was a disk. I don't remember.
Okay. And was the block storage technique developed there?
Yes. Blocks were a convenient size. Sectors were too small. So a block gave you a reasonable amount, 1K byte, for storing a portion of the code. And an application would typically be 20, 30 blocks.
Right, okay. One of the unique features of Forth being, of course, that applications are stored in their source code form, generally speaking, anyway.
Yes.
So it was at this time then, am I right in thinking that it was at the observatory that you met Elizabeth Rather?
That's right.
So how did you come to meet Elizabeth? What was she doing at the time? Because of course you were the world's first programmer, and it's quite widely known that Elizabeth was the world's second fourth programmer. So I'm interested to know how that came about.
Well, Elizabeth's husband was an astronomer, so he was at NRAO and doing observing. And she was working at a computer center. In Tucson. Ned Conklin was the chief of station at Tucson. And somehow her husband and Ned got together and they decided that they needed support in Tucson whilst I was back in Charlottesville. So they hired Elizabeth to provide that support.
Okay.
So she was kind of appalled at this weird language. but picked it up real quick and was excited about the potential.
Right, yeah, that's new to me. I kind of had the impression that she was always there, and so she was witnessing the evolution of the Forth system as you developed it. You're saying that's actually not the case, so she was hired and would have come in cold, not knowing anything about Forth.
Right, she came in about a year after I started the Tucson project. And she was the salvation of it, because it probably would have withered and died without her enthusiasm and without her support. The people back in Charlottesville were not happy that I was developing my own language in this strange fashion. And indeed, one of the other programmers in Charlottesville said, well, if he can develop a language, I can too. So he wanted to develop his own language.
Fifth.
And things were getting out of control. So the management sort of clamped down. And that's one of the reasons that Forth Inc. got formed. Forth Inc. was formed with the Rathers and then Conklin and me, sort of out of frustration with the administration of NRAO, and also seeing an opportunity for commercialization.
Okay, I'd like to talk to you about that, but just before we do, I'd like to take you just back a little bit, because if my research is correct, just prior to the incorporation of Forth Inc., the Forth language itself was already beginning to enjoy a modicum of success in its own right among the observatories. Is that true? That
Yes,
was
that's
prior
right.
to. And how did that come to be? Was that just chat amongst the scientists and the people working at the various observatories, exchanging information and saying, hey, you need to check out this new system that we've got?
That must have been the case. Again, John Rather was an astronomer and was a networking type of astronomer. I know that the first independent Forth was developed at Caltech, again for astronomical purposes.
When you say independent, you mean without your involvement? Is that what you mean?
I maybe shared the source code with them or something like that.
Right.
But it was Caltech Forth, and it didn't have much to do with me. And then there was a version at Arizona State, which was also in astronomy. And it spread. It became an official astronomical community language,
Right.
which was very reassuring. But those times are past. Now everyone uses C.
Right, but presumably you had, at this point where there was a bit of an inertia beginning to build up behind the language, you're obviously observing this.
That's right.
Elizabeth is observing this. Is that when the first inklings among you began to sort of emerge as, hey, maybe we've got something here that could be a success in its own right, as an independent?
It became clear that you could program in Forth much more quickly and have more efficient programs than you could with the other languages, which were, there was APL and there was Algol, and of course Fortran. You know, all of these new languages were going to replace Fortran, and Fortran still exists today, running mostly the programs that were developed way back in the 70s. Curious.
So if you can develop software and test software in a fraction of the time, in real time, there's
Exactly.
commercial value in that, right?
That's what we were hoping. And that's what proved to pay out. Forth Inc. could do an application in 2 weeks that otherwise would have taken a year. And there was a market for that at the time. Of course, it had to be marketing. We were certainly less successful with marketing than Bill Gates was. And we were in competition with him, although we didn't realize that. If Bill Gates hadn't stepped up with Microsoft, Forth might have had a much different future.
Okay, let's take just a little bit of a step back. So you're at the observatory. Forth has an inertia behind it. It's becoming clear to you that there's some commercial value in that. Who was it that said, you want to start a company? Let's go and do this on our own.
Well, it was either Ned Conklin or John Rather, or the combination. Ned was leaving NRAO or at least leaving Tucson, and John Rather was going to Los Angeles, a think tank, I believe. And so there was going to be change. And we took the opportunity of this change to form Forth Inc. And we all moved to Los Angeles.
Okay, so that must have been, so this would be 71, 72, I guess.
Yeah,
You've already said that clearly you were married and you had a baby at this time.
yeah, it was another gamble.
So that must have been a bit of a leap to...
We had financial backing
okay.
from Ned Conklin of $5,000. So we were starting on a shoestring and counting on generating revenue.
So how did you go about, so not only is it a new business, but it's a new business in a different geographical location, because you've moved to Los Angeles, so you don't know any of the companies that are in that area that you might market to. So how did you go about generating business?
I don't know. We did hire a marketing manager, or eventually we hired one, but I think that came a little bit later because we had to get a couple of projects. I think the first projects involved programming telescopes.
Okay.
So we had this entree, and we had a package that could control a telescope, and we merely had to port it from one telescope to another. Again, the telescopes were just being automated at the time, and there was an opportunity to cut the development time from a year to a couple of weeks. And that got us enough funding to carry us over into the next stage, which was commercial applications.
Okay, so now Forth is reinventing itself to a certain extent as just a general
Yep.
I'm going to sit as well.
software house.
Can
Would that be right?
Cut
Should we
that?
pause there? So Forth was reinventing itself as a general purpose applications software development house. Is this when Polyforth came to be? In the sense that you design, am I right in thinking EuroForth was the internal platform that you used to develop general purpose applications, which later became a product in its own right?
That's right.
Okay.
Polyforth ran on mini computers, and I ported it to many different mini computers. This was a time of the evolution of small computers, and they were all different, though not in hugely significant ways. But people were buying these computers, and there was really inadequate software support for them. Much less support than you get now from computer manufacturers, which is hardly adequate now. And it was basically zero. So people needed companies like us that could do software, and we could do it super fast. It would take me about a week to port Polyforth onto a new computer, almost independent of whether it was a model I'd seen before or a completely different model. It still took a week to port it over. Whereupon all of our Forth tools were up and running, and an application programming was another week.
You're taking advantage of the fact that once you have the fourth, or what I call the fourth nucleus, which you would write in assembly language, the rest of Forth is written in Forth.
Right.
So there's only a reasonably small portion of the kernel, for want of a better word, that you need to sit down and write from scratch for each platform.
Yeah, the kernel was about 1K or 4K in that range. And everything else was high-level Forth.
So once you can interpret a block, you're off. Once you have the disk access,
It was
up.
a very satisfying experience.
Is this when you were carrying the famous portable Forth development system and microfiche records?
That's right. We kept records of all the applications we had done on microfiche. I had a portable microfiche viewer, and when I needed some code from an earlier application, I could just retype it from the microfiche. There was no decent portable media for transferring data from one computer to another. I'd forgotten about that. I had that microfiche for a long time, and I don't have it any longer.
Oh, that's a shame. It would be nice to be able to resurrect it and put it online or something.
I gave a lot of stuff to the Computer Museum in San Jose. Maybe the microfiche was amongst it.
Maybe we can try and find out.
I know one of the first things we did commercially was a database management system.
Right, Elizabeth rather refers to this quite a lot, and has referred to this in some private correspondence with myself. It's something that seems to be something she's particularly proud of.
Uh-huh.
Can you talk a little bit about this database system, why it came to be, and some of the features of it,
Well, this is
and maybe the state of the art of databases at that time?
yeah. This is early days again of database management, and there was something came along a bit later called a relational database.
So there was no real established way of representing a database at that time. SQL was not a thing then.
We just invented it as we came along. Art Gravina commissioned us to do a system on a mini computer where you had many terminals. And my experience with order entry persuaded him that we knew what we were doing. So he gave us a shot. We came up with a very nice system. I think we had 32 terminals and a 300 megabyte disk drive, and they were storing transactions, and they needed to search the database and prepare reports and get quick access. So we provided indexes into the database sorted by alphabetic or order number or whatever, and gave very, very fast access, 10th second access to any data in the base. And we could run 32 terminals at full speed. At the same speed you could run one terminal. And nobody else could do that at the time. And he was very successful. He did medical databases and marketing databases. That was a good application. Now I was a bit disappointed. I wanted to do astronomy, and I didn't really much care about commercial, but that's where the money was.
Right. So the database system that you designed, which was used for example, in medical database systems, did Forth reap any of the rewards from the commercial success of that? So it sounds like it was quite an abundantly successful commercial venture for, I'm sorry, can you say the gentleman's name again?
I don't think so. We were paid to do the programming.
Just a one-off.
And the intellectual property rights remained with the customer. We weren't selling Forth as a tool for people to use. We were selling applications. And Forth was our secret weapon that got us the applications. That probably was a mistake, but that's the way it was.
Yes. And what were the hardware platforms of the day then? You mentioned 32 terminals. Was this something like a PDP-11 or something?
I think he used something called the mod comp, but it was the class of the PDP-11.
Okay. So you've already mentioned there that you weren't that much interested in developing commercial applications, but that's where the money was. You presumably did that for a number of years. What memorable projects do you recall from your time at Forth Incorporated?
Well, the neatest one was an animation camera for Hollywood. We did some of the animation for a movie called Battle Beyond the Stars, which was a remake of The Magnificent Seven in space. It was fun. The thing was that you've got a camera, you need to control the camera in such a way as you can track a spaceship as it crosses the background and do it many times to within a pixel so they get the proper overlays and effects. And so I spent time in a sound studio in Hollywood programming this camera swinging through the sky. That was fun. That took a little longer than the usual application. I think that was a month or so of something completely different. But again, Forth was a good language for that because it was fast, it was efficient, and it was flexible. You could describe how you wanted the camera to move and it would do that. I also did a sound editing, video editing studio application where you're putting up images and mixing sound with it, and that was fun. Those are good people to work with in Hollywood. So I've applied Forth in an academic and a commercial and an entertainment area, and it was effective in all of them.
And remains so. So you've told us a little bit about some of the projects that you've worked on at Forth Incorporated. Clearly you have some fond memories of the projects that you've worked on, and yet you decided to move on from Forth Incorporated to pursue another avenue, the next generation perhaps of Forth.
So we cut there. We got him.
So you've told us a little bit about the Forth projects that you've worked on at Forth Incorporated. Clearly you enjoyed your time there, but you did decide to move on from Forth Incorporated, and you left Forth to pursue an interest, I believe, in implementing Forth in hardware. Was that specifically the reason that you left?
Yes.
Now, I'm interested that what interests me is that it seemed necessary, correct me if I'm wrong, for you to have to leave Forth Incorporated in order to pursue that. So was there some resistance to you pursuing that within Forth Incorporated, to the extent that you felt that you had to go it alone to do it?
It got complicated, as everything does. Somehow we encountered a man called John Pierce, and he established a company. He was interested in Forth for some reason. He established a company to develop Forth hardware. In the course of doing this, he bought Forth Inc. So Forth Inc. was involved with this hardware development.
Oh, okay.
And he was providing financing. In fact, that's about all he did. He spent all of his time financing. Eventually, Forth Inc. bought themselves out of that deal. It didn't turn out to be satisfactory. But at the same time, we had developed the Novix computer chip.
So that development took place at Forth Incorporated?
Oh, sort of all mixed in together. To develop the chip, I had to be in Silicon Valley. And so I moved to Silicon Valley, and Forth Inc. stayed in Los Angeles. And partly because I was getting bored. The applications were fine, but I had done the applications. I didn't need to do them again, and I wanted to do something more exciting. Besides, I had this theory that software was in a real rut. Nothing exciting had happened in software for 10 years. Hardware was where it was at. Hardware was dynamic and aggressive and changing. New generations of hardware continually coming out. And I was interested in getting onto that cutting edge. I was wrong. It turned out that hardware development is even more conservative than software development, but that's not the way I saw it at the time. So I used Forth to design the Novix chip. Not actually the layout, but the architecture. And I simulated it and proved that it would work and give certain performance levels. And so we made a chip.
But did you have any background in electronics prior to this?
No. I had read a book.
You read a book, and then you went off and developed your own chip.
It was called, it was by Carver and Mead, about CMOS chip design. And I read the book and I said, I can do that. And so I did, and I was right. Now, that's the only reason that the Novix chip and other Forth chips.
Sorry. We'll cut that out.
That's the only reason.
That's Paul having heart failure over the fact that you read a book and then went on to design your own chip.
Yeah.
We just cover that again. Yeah, we can cut that bit out.
If I had known more about chip design, I wouldn't have been able to develop these chips because they didn't follow the rules.
Right.
Everybody
You've been
knew how to do
constrained
chips.
by the way chips are designed.
Yeah. So this was a fresh look at it, and it proved to be very successful. The Novix chip was a 16-bit chip with 16-bit instruction and various fields, bit fields in the instruction that could implement various aspects of Forth words. For instance, a shift or an add or a logical operation or a conditional. They were all built into this one instruction.
So you could do something like a dupe and an add simultaneously, or at least in one instruction slot.
That's right.
Okay.
It was the duty of the programmer to pack as much into an instruction as he could, and thereby maximize the execution speed. It worked. It was good.
But it wasn't a parallel processor, is that right? So, but it could fetch multiple instructions in one fetch and then sequentially execute them.
No, it was a single instruction, but that instruction could do parallel things.
Right, okay.
But I don't know.
Similar to what the ARM can do. I mean, the ARM can execute an instruction and do a barrel shift, for example, at the
Yes.
same time.
Also similar to what the B5500 was capable of doing. These were my models, if you will, for how computers should act.
So there was some prior inspiration.
Did we apply for a patent? I don't recall. I think we got a couple patents out of Novix. And then Piers was unsuccessful in his continuing financial endeavors and sold the technology to Harris. Harris produced a chip called the 2000 Express, 4000 Express, in a rad-hardened process, which has been used in a lot of space projects.
Still used today, I believe.
Now that chip was different than the Novix, but it used the Novix architecture, and
Corrected a couple of bugs, did it not?
I'm sorry?
Did it correct a couple of bugs that were in the original Novix?
The Novix had a problem with interrupts, and another problem with multiply, which were vastly overrated. It didn't really amount to much. But Pierce could not come up with the money to make a new Novix. And so the ball passed. I was frustrated by the Novix project kind of ended. None of these projects ever end. They sort of wither away.
Yes,
And
then
there's
morph
never a
into something
clean
again.
ending. But at some point I left Novix and I was going to design my own computer, and it was going to be a 32-bit version, or 32-bit version of the Novix with a 32-bit instruction, and more fields and more whatever. I worked on that for a year or two, and nothing ever came of it.
Can you tell us a little bit about the how the design of a chip was done then? What years are we talking about? Are we talking early, late 80s, early 90s?
Novix was sort of middle 80s, I think.
Right.
85 or so.
So were you still laying out on with tape then, or did you have computer-aided tools?
We contracted with a company in Scottsdale, Arizona, who had experience with designing gate arrays. So the Novix chip was a gate array, and there were tools you had to use to design the gate array. And a man named Bob Murphy was responsible for doing that. I was responsible for designing the architecture, the instruction set, the registers, the stacks. And he implemented that in the gate array. Very, very successful collaboration. My fourth code was basically a simulator of the instruction set running through the architecture. It didn't produce a design. It produced, what did it do? It validated the design. And that's how the bug in the interrupt came in, because you couldn't test interrupts in the simulator. Interrupts are random. So this was my first introduction to silicon design tools, the industry standard tools. I found them unsatisfactory, but it's sort of a classic that the silicon people insist you use their tools because they trust them, they have been calibrated, and foreign tools are not welcome. That's still the case today, even more so. You must use industry standard software. But there was a slip-up somehow. It was a service called Moses it was at Caltech at the time, that let you prototype chip designs. And it cost about $5,000 to produce 20 chips. I took advantage of that and had an account with Moses for a while. Green Arrays still has an account with Moses. The technology at the time was 3 micron 3,000 nanometers. It's now down to 8 nanometers. Huge shrinkage of the process. But it became more and more opaque to an independent designer like me. At the time I was working with Moses, for $5,000 you could get the chips. Now, the new processes, if you can get access to them, cost you 10, 20 million. So it's completely out of range of any independent or even a small company like Green Arrays. But at the time, it was exciting. When you submit your chip design, you get chips back in a couple months. Is it going to work? Cross your fingers.
So your experience with designing the Novix caused you to detour slightly back into software development in order to correct your perceived grievances, shall we say, with the tools of the time that we used to develop hardware. Would that be right?
Yes. It's always been a back and forth between hardware and software. The software developed the hardware. You had to implement Forth on the new hardware in order to design the next generation of chip. And that was very productive, informative.
So from Novix, EuroForth was born. Would that be true?
No. The first came Shaboom. I was gonna design a 32-bit machine with 32-bit instructions. Russell Fish persuaded me to use 8-bit instructions and pack them 4 per 32-bit word. And that led to a completely different architecture. Well, completely different instruction set. The architecture was the same with 2 stacks and a CPU and some kind of I/O.
So again, that chip was designed with industry standard tooling.
Shaboom was designed at Oki Semiconductor, Oki Design Center. I had to use Oki simulators to verify the chip design, but I could use Forth to design the chip. No, I couldn't either. I had to use Oki layout tools and all. So this was my second exposure to standard industry software. And it was...
But now you're doing the layout.
I was doing the layout. And it was painful, but frustrating. I could see it could be done better. But we got the chip and it worked perfectly, I think. And Fish was going to do the marketing. I was doing the design. And the design was incredibly successful and the marketing was a failure. Again, you build a better mousetrap, the world does not beat a path to your door. You have to pave the path for them. But Shaboom was the first chip I designed with stacks on the chip. Novix had external stacks in memory chips, which was very clumsy. In fact, Harris took those stacks and put them on their chip. So that informed me that the stacks could be on chip. Harris stacks were very deep. Harris had 256 deep stacks. The Shaboom had, I think, 16 deep stacks, so a very shallow stack. My current designs have 8 deep stacks. Stack doesn't need to be deep, it just needs to be present.
Yes, I can't. Certainly on the data stack, if you need more than 8 slots on your data stack, you're probably doing it wrong.
Yes. If to do deep recursion, to recursively compute the Fibonacci series, you need huge stacks, larger than anything you can put on hardware. So you have to have a software implemented stack.
Yeah.
But you can always do that.
So okay, so unfortunately the Shaboom was not successful. But undeterred, you moved on to the I-21. Would that be correct?
Shaboom was not marketed successfully, but it did lead to 10 or 20 patents. So it was very successful as a patent vehicle, so not as a computer chip.
So were you able to derive some income from that?
Eventually, that came along later.
Oh, that came later. So you're still kind of struggling here to make ends meet, I presume. Looking for a project that's going to pay off nicely.
Yeah, the Shaboom was developed on, again, a shoestring. No money up front. It took about a year, again, living off savings. Then there was another project came along. It was an internet appliance. This was in the 90s, and internet was just blossoming. So we formed a company to build a little browser email around a video tube and programmed in Forth and running a chip. This was the I-21.
This was I-21 and the company was ITV, is that correct?
Yes.
So is this was this with Jeff Fox?
Jeff was involved in that. Gary Langstrom was the president of this new company.
Okay.
Jeff wanted a chip which could be networked, and that was the F-21. These chips had the same computer basically, but different I/O capabilities. One aiming at graphics display and one aiming at networking. This computer, let's see, derived from the Shaboom, but it had 4 5-bit instructions in a computer word. And 2 stacks and the CPU and on and so forth. No, Ting's chip came first. The P-21, that's right. The P-21 was the first version of this architecture developed for C.H. Ting, who saw uses for it in managing displays. I think he sold them to people in Taiwan for signage. And he made, once we got a successful chip, and it took several $5,000 prototypes,
Okay, hang on a
I
second.
think he made 20,000.
Okay.
I don't think he ever made back his expenses. I have termed myself a Jonah, that I will design these beautiful chips that are not commercially successful. My latest chip was the GA144, which has not been commercially successful yet. We still have hopes.
Sure.
But they were good chips. They worked, they were fast, they were low power. I don't know what more I could have done.
Yes. Well, as we know, it's not necessarily the best hardware that becomes the most popular. We know that from the current state of the world, shall we say, with
Yep.
Intel. Okay, let's take a little bit of a step back. So it was Jeff Fox is, in my opinion, there are a number of individuals in the Forth universe that are landmarks along the journey of Forth. Yourself, there's Elizabeth Rather, Ed Bailey, and one of those people that I believe made a significant contribution to Forth is Jeff Fox, who's sadly no longer with us. I was just wondering if you could recap how you came to know Jeff and the projects that you worked on together, what your relationship was like.
I don't recall. It must have been through FIG, the Fourth Interest Group. There were a lot of the, I can't tell you the history of FIG, but it was formed in the late 70s, I think, and an enthusiastic collection of people in Silicon Valley, and it spread to Europe and Japan and China, and then gradually died away. But Jeff was a shaker and mover in Silicon Valley. And he commissioned this F-21 chip, partly because of his own ambitions, and partly, I think, as a charity gesture to me.
Okay, to bring some work in for you, some paying work, as it were.
Yeah.
Okay. So was it strictly a business relationship between you, or did you become friends?
It was just friendly. I think I signed a contract with him, Fox Enterprises, something like that, to design the chip, and I think I fulfilled the contract.
Right. So was the F-21 a precursor to the multi-core chips?
The which chip?
Sorry, not the F-21. The chip you designed with Jeff, was that the precursor to the multi-core chips that you...
Yes.
Okay.
Yes, that's right. Things were kind of at a standstill come around 2000, the year 2000. When it occurred to me I could put multiple computers on the same chip. These chips were an embarrassment. You couldn't have too small a die, or you couldn't handle it. You had to have a certain size die, partly because of the mechanics and partly because of the pads around the outside. So my die were mostly empty. Now other people would fill that with memory, but I didn't know how to design memory. So I thought I would fill it with computers. And the first version had 24 computers, an array of 4 by 6, I think it was, that could talk to each other. And it was a networking, a truly parallel processor. And it worked well.
Each one being its own individual fourth machine.
Yes. Each one had a little bit of memory, 64 words of memory, and then the standard stacks and CPU that I had been using in the F-21. So the new thing here was the memory. And I had to design a 64-word memory, which I managed to do. It worked. It has been improved since. It would be hard to make it larger than 64 words.
Okay. What's the constraint?
You've got to drive large capacitance in the memory. And you have to have address decoding to identify a particular word. And this is a long time solved problem in the silicon world, but it's not known to me. To put someone else's memory on your chip is a real hassle. It can be done, but it's not, I can't do it.
Right. Okay, that's interesting. So that's the primary constraint with the current generation of multi-core chips then. The memory constraint at least.
It means these computers are tricky to program. But I don't think it's really a constraint, I think it's a feature. Because it encourages you to write small, compact code. I think if I doubled the memory, people could not do any more, they could just do it more easily.
Right, okay. Programming does force you to plan and factor not only at the software level but at the hardware level.
Right.
You plan your path across the chip and what each node is going to do. So it isn't new. I don't like to use the word paradigm, but it is a new programming paradigm for most people, development paradigm, I guess.
You must learn how to coordinate the activities of many computers, each one of which cannot do very much. It's not like an Intel core, which is a full-blown Pentium. It's a tiny computer. But tiny computers can do remarkably a lot of things, especially when you have many of them. The 24-bit, the 24-core chip turned into a 40-core chip. And this was a company called TPL, with Dan Leckrone as president. And
So we're entering into a somewhat controversial phase of fourth history.
one of them, yes. it's at this time in developing the multi-core chip that Leckrone discovered there's some value in the patents from Shaboom. And so he started licensing these patents and did so very successfully, ultimately raising some, I think, $200 million in license fees.
Did any of that success find its way to you?
I was supposed to get maybe 50%, and then that got negotiated down to 25%. And eventually I ended up with about 5%. And this was not acceptable. So controversy erupted. And 5% amounted to about $11 million, so this was not nothing. I should have been happy with it, but that wasn't our agreement.
Right.
And so I protested. I wish I had the $11 million now, but it's long since been dissipated. Not foolishly, but unfortunately. On the other hand, if I had $11 million, I would have invested it in a new chip and probably lost it anyway, so what the heck.
You did manage to fund the incorporation, but I guess we'll stick with TPL just for a moment. Am I right in thinking that that the controversy has now been settled in a legal manner? There was some litigation.
There were lawsuits back and forth, and they eventually were settled.
Right.
Lawsuits are a lose-lose situation. The only one that wins is a lawyer.
Yes.
But sometimes there's no recourse. Another company was involved called Patriot. Now, Fish and I were co-inventors on the patents. And Fish sold his interest to Patriot, and I kept my interest. And this led to a conflict and an ultimate resolution and a joint venture and patents and litigation, all very complicated, all very unsatisfactory. From my point of view, a waste of time. But it did lead to the multi-core chips.
Yeah, so I mean, presumably while you're involved in litigation and having to make depositions and get involved in the minutiae of the various legal cases, you're not designing.
That's right. But I did collect a wonderful team of Forth people to design and program the 40 core chip. Jeff Fox was involved, and Greg Bailey and Dean Sanderson, and it was a star-studded team which did great work, but it did not impress Leckrone, and he terminated it, which was another source of conflict. But out of that was born Green Arrays.
Right. So some of the income that you managed to derive from TPL, was some of that used in order to form Green Arrays? Seed funding, for that kind of thing? Or was it shoebox money?
I forget. We tried to make a deal with Leckrone where he would provide financing, but he wanted control, and the whole problem was his control was destructive. So Green Arrays went off and got some scratch funding from angels, and designed the 144. It did not, Leckrone did not like that. He thought we were stealing his intellectual property. But that was not the case. And it would lead more lawsuits, but that hasn't happened.
So that's just to clarify, that hasn't happened.
It hasn't happened.
Right.
It
Was that
still
because
could, but it won't.
is that because you're able to satisfy him that it wasn't the case? Or?
No, I think we satisfied him that we were not commercially successful, so there was no point. You can't sue someone who has no assets. I mean, there's no point in suing someone with no assets. And Green Arrays has a wonderful chip and no market. No market so far. Still promising applications.
Right.
The market is not quite what I expected. I was designing this chip to be a clean, lean, mean fourth chip. It turns out it is a very low power chip. And the market is in low power, not in fourth. On the other hand, fourth was required in order to make it to be low power. So it all hangs together.
Okay. So when you say it's low power, can you put some figures on that? A typical application.
The only number that comes to mind is 7 picojoules per instruction. It's on Green Array's website. As of a couple of years ago, it was the lowest power computer in existence by an order of magnitude. I don't know the situation today. I've not been tracking it. The MPS has a very low power, they promote a low power microprocessor. It's 10 times the energy of us. So how do you use this chip in order to take advantage of the low energy? I think it'd be great for artificial intelligence, but we haven't found that killer app yet.
That could be the killer app. Could be.
Okay.
Something that needs to be able to scale up, highly parallel. The inferences are quite clear, are they not? But just going back to what you were saying about the potential for legal action to be taken in the event that Green Arrays was suddenly successful, does that not provide an impetus to come up with an alternative design, maybe a new architecture, in order to protect oneself against possible legal ramifications? The greatness of the design notwithstanding, is presumably a desire to extricate yourselves from that potential risk.
You're right. It would be nice to do that. I don't have any idea of what a new architecture could be. I've shot my wad, if you will. And besides, I don't think that would head off a lawsuit. Lawsuits do not need to be rational. You can sue anyone for any reason, and it's up to a judge to decide. So, we redesigned the 144 using new tools, using SwiftForth, for instance. No, SwiftForth. Using SaneForth instead of, and ColorForth instead of SwiftForth. We redesigned everything improved the design. Made all the changes that were possible. And I think we made enough. But again, it's not my call, it's the judge's call. I don't want to go there. It's just too painful.
So that brings us to the present day. I'd like to mention.
Okay.
So just a quick recap on green arrays. Another fourth luminary is Greg Bailey. I was wondering if you could recount how you came to meet and know Greg and indeed work alongside him at Green Arrays.
Well, I think Dean Sanderson was the first programmer that Forth Inc. hired. And Greg and Dean were a pair. And so Greg got involved with Forth Inc. and have been involved ever since in Forth applications. Greg has a company called Athena, which has a number of successful Forth applications dealing with the internet. And he's the president of Green Arrays. Green Arrays, once upon a time, had maybe 12 people actively involved. Now there's about 6, scattered all over the world. It's easy to have these remote collaborations with the internet. And again, I think we're taking advantage of this cutting edge technology.
So is there, what would what do you think next is, what is next for Chuck Moore and Green Arrays?
Well, I'm the chairman of Green Arrays, which is a ceremonial post. To all intents and purposes, I'm retired, but it's possible to come out of retirement. Green Arrays has a couple of exciting opportunities which might come to fruition. One of which will be a new version of the 144. I think it's going to be called the GA 144A13, and I don't know why.
Can you talk a little bit about the chip?
About the 144?
The new version.
The new version will have lower power applications. At the moment, sometimes we have to sit and spin waiting for an event to occur. And that uses power. If we don't have to spin, we'll cut the power significantly, and that will be nice. We also need more communication between multiple chips. On our development board, we have 2 chips, and they can talk across a high-speed serial line. But there's only 2 high-speed serial lines. We want to have 6, so that will lead to Now that's one direction. Where I would like to go is to a small geometry. That would draw me out of retirement. If we could get down to 14 nanometers or 10 nanometers with I could put 10,000 cores on the same size die as we have now. And I think that would be a qualitative change. 10,000 computers that you could program. What would you do? How could, it's somewhat mind-boggling. We could do that. But two requirements. One, you have to have the $25 million or so to make a prototype. Second, you have to persuade the fab house that there's going to be a significant volume to be worth their trouble. And significant volume means, what, millions. So we'd have to have the killer app plus the money, and they're not in sight. You mentioned sourceless forth.
Yes.
That is my current interest.
Is it? I'm surprised to hear that because from researching online and watching various videos of your fireside chats over the years, I know it's something that you pursued, but I thought you abandoned it. It was a journey that you went on, and you're not convinced of the value of it. Are you saying that you're re-evaluating that?
I'm re-evaluating it. It still isn't clear that there's an advantage. But I go back to the adage, the map is not the territory.
Okay.
And the fourth source code is a description of the program. It isn't the program. And translating it into the program is not completely satisfactory. It would be on a fourth computer, like the 144. There's a one-to-one correspondence between source and object, and that's the end of it. But I like the notion of a decompiler. You've got the object program, and you scan it and generate what looks like the fourth source. You just turn the process backwards. The advantage there is that you eliminate the source. Instead of having two files, source and object, you only have object. So you've cut the overhead of an instance of an application in half. Big deal, is memory's cheap. So that was always kind of marginal. But recently I've come up with a new way of programming the PC. The PC only has one stack, and adding a second stack is most inefficient. What I'm doing is using the 16 registers as a stack, and explicitly putting things in the register that I want. The way to do this without violating the fourth appearance is to have superscripts. The fetch operator would fetch from an address in register 0 and put the result in register 0. If you want to fetch to register 1, you put a superscript 1 on the fetch sign. And so on, using superscripts to indicate register sources and destinations leads to a very pleasant appearing decompile.
Yes, I'd imagine that's quite a nice notation to read.
And I want to experiment with that.
So just to be clear, you're not sitting at a keyboard tapping hex in, or are you?
No, it's octal.
It's octal.
Octal is much more comfortable in the Intel instruction set. But
That requires you to memorize the opcodes.
no, I've got a fix for that.
Okay.
You point to an instruction, the opcode is decoded and the description is shown to you. Like this is an instruction that fetches from register 1 and stores in register 2. Again, it's a work in progress, and I'm not, this is a possibility. That's something I'll work on. The other thing I want to do is a native forth on the PC, which means I have to go to UEFI instead of BIOS. And I don't know how to do that, but I can work on it. And the fourth thing I can do is nothing. So I'm sort of neutral as to which of those futures will pan out. I'm easy. I'm not going to bust the gut.
I think I'd like to see 10,000 fourth cores on a single die. I think that's...
Help us raise $25 million. Or make a deal. I don't know anyone actually pays that. You make a deal with the fab, and they, in exchange for promising them huge volumes of chips, they will negotiate. That's not my part of the business.
Yeah. But I think we'll leave people to think about what they could possibly do with 10,000 cores on a single chip. I think it's probably a good place to leave it. And I'd like to thank you for coming to Edinburgh on behalf of the Forth user group. And it's been a pleasure to talk to you today.
It's been fun.
Thank you.